We are studying substitution reactions at aromatic compounds, and one of the mechanisms that we study is electrophilic aromatic substitution. In this reaction, we'll always have an electrophile of some sort, but what is important here is that you will have a nucleophilic attack by the pi electrons in the ring. And this, after several steps, what you will form first an intermediate, let's do it, He. Here you will have a positive charge. And that's a sigma complex. Here you have several resonance structures. And then, and depends on what is the reaction that you're doing, you will have a base, removing the extra product. And your product is finally aromatic again, but you have replaced the H by an E. But what is important here is that this is a nucleophilic attack by the ring. So the more electron density that we have on that ring, the stronger the nucleophile. So when we have substitution at the ring, that affects the rates. So say that benzene is your baseline. So some substituents will make the reaction faster. And say, for example, if we have toluene, and let's make that explicit, toluene is methyl benzene. Say that you're doing a nitration, NO3, H2SO4, that's the condition. So we have two things. One is reactivity, so how fast this reacts respect to benzene, and where is the nitrogen group going to be? So reactivity. So when we have alkyl groups, we have typically this group work as weak electron donors, and therefore they're making the nucleophile, which is the aromatic ring, stronger. So alkyl benzenes react faster than benzene. So I'm going to write it down. So alkyl benzene. So they react rates. So this is greater than benzene rate in electrophilic aromatic substitution. Therefore, we call this activating groups. Now, another thing is that where is the substituent going? So I'm going to now change. I think I did another video in which now I'm going to use another activating group. Let's say that instead I have a methoxy group. So this is anisole. And here we know that we can do resonance structures in which I can place negative charges on both. Say I'm labeling the positions. When you do that, you're going to have negative here or here or here. Meaning in the resonance hybrid, you will have partial negative charges here. So delta negative, and delta negative. And let's do, so positive here, because we did that. And let's say we have that. So we have the charges dispersed, but the places where the most negative charge is here. So activating groups are ortho-para directors, because essentially they direct in those positions because those are richer in electron density. And again, since this is a nucleophilic attack, that substitution will happen where you have the most electron density. And when you have activators like this, or activating groups, they will direct ortho-para. Now, if that's the case, what is the product here? So predicting product, if this is anisole and you will have more electron density in ortho and para, we will have here a mix of products. So here is anisole and you will have ortho. The electrophile here is this. And so you will have ortho substituted, so ortho nitro anisole in the other product. is a para substituted. So this is the para nitroanisole. So you will have a mix of products. In all of the activating groups will be ortho-para directed. So summarizing, what are the activating groups now? Here, those groups that make the aromatic compound react faster than benzene. So we have, say, weak activating and stronger. Here you have the alkyl groups. And we have some moderate activators and some stronger activators, but the stronger effects, say moderate to stronger activators. You will have, for example, groups such as OR, so ethers. You will have OH. You will have also moderate to weak, I'll say, amides, esters that way. Or you can have also, say, with a nitrogen, you can have an amide attached to the aromatic ring. So this is the aromatic ring. So all of those groups. All of these groups, the predominant effect is donating electron density to the ring. So there will be activating, so all of them will be activating, but it's stronger than the alkyl groups, and ortho-para directing. And that will be important when we are predicting products. We're going to be doing more in problems about this topic.